We always start from lowest energy to highest. And if we needed to figure out how many electrons there are in an atom and it's neutral, we can use the atomic number. So as we talked about earlier, the atomic number, which is the number of protons, will tell us the number of electrons if it is neutral. So we could kind of just go by that. So let us do that. So we'll borrow our chart here from the book. And again, we always start up here. We'll start with the very first one, which is hydrogen. And hydrogen has one electron and it has one proton. So it does have one electron. So starting up here, that takes us here to the 1s. And it would be 1s1 would be the electron configuration for hydrogen. Once again, here, the very first number tells you the energy level. That's that N number. This letter tells you the orbital or subshell that the electron's in. And the very top number tells you the number of electrons in that orbital or subshell. So it should be written like that, kind of regular size number, 1 in front, lowercase letter, superscript up on top, number. So if we were to sort of visually look at the electron here in this orbital, and this is what is sometimes referred to as orbital diagram, kind of a visual representation of the electron. We have like a box or a line that represents the 1s orbital. We basically have just put into that orbital one electron, right? And we know that each orbital could hold 2, which means we still have room in that orbital for one more electron, right? So let's do that. That is helium. Helium is 2 electrons. It is the atomic number 2, which has 2 protons. So to match it out would be 2 electrons. Once again, we're always going to start up here at top. So we're coming to our 1s orbital, and this would be a 1s2 at this case. Again, what this is telling me is on the first energy level, hanging out in an s orbital, I now have 2 electrons basically hanging out in there. So again, you can think of it like we were talking about, maybe like a hotel or something like that, right? The n level is the floor. The s is like the room, right? And how many people maybe are in there, electrons are in there. If we were to sort of show this orbital diagram here of picture-wise of what's going on, this is what is sometimes referred to as an orbital diagram. We would have an electron going upwards and we would have an electron going downwards. Not relevant for our class, but there's a reason why one goes up and one goes down, and it has to do with quantum numbers, which obviously we're not going to get super into at all, and what's known as the Pauli exclusion rule, which basically says those electrons have to be spinning in opposite directions for them to be in the same orbital. They cannot be going in the same direction. They always have to go opposite of each other. That is what is sometimes referred to as those electrons have paired spin, and they essentially cancel each other out, basically. At this point, can I put any more electrons into that 1s orbital? I cannot. That means my next electrons has to go into the next lowest energy level. And that would happen at lithium. If we go to lithium, has 3 protons, which means it has 3 electrons. Once again, here we're going to start at the top, just like we did before. We're going to go to our 1s again. So 1s2. We're now going to zigzag back here, and the next lowest energy is 2s. And we need to put only 1 electron in. If you count up the top numbers, that tells you the total number of electrons you've distributed. You put 2 in the first one there and 1 in the second. That's a total of 3 electrons basically has gone in there. If we were kind of going to picture it up here, we would have a 1s orbital. We would also have a box that represents a 2s orbital. Not correct in energy, but we'll go with it. We put 1 up, 1 down. And by the way, the first electron that goes in an orbital is always pointing in the upwards direction. How many more electrons could I put in that 2s orbital before it's full? Yeah, 1 more until it's full, right? This also tells me a couple of things when I look at the electron configuration. How many electrons do I have on the first energy level? I have 2 on the first energy level. This number tells me the energy level, and there are 2 electrons on that energy level. How many electrons do I have on the second energy level? I have now 1 on the second energy level, right? So I have 1 electron that's higher in energy than those 2 that are lower. Yeah. As we'll talk about, that higher in energy in the case of lithium here is what is known as the valence electron. It's that higher energy one. The ones lower down in the lower energy level are known as core electrons. They're closer to the nucleus and held tighter. As we'll talk about, valence electrons are important in bonding, and those are the ones that are involved in bonding. So continuing on here, after lithium, we got beryllium, which again, if you look at the periodic table, has atomic number 4, which means it has 4 protons, should have 4 electrons, always beginning back at the top here. So taking us to our 1s2, zigzagging back again here to 2s2. Again, if we count up the top numbers, 2 on top of the first one, 2 on top of the second one, that is 4 electrons we've just put in there. Again, picture-wise here, 1 goes up, 1 goes down, and our 2s up and down. As we can see, we are now full on that 2s orbital. Where would the next electrons have to go after that? Yeah, so again, just following our little scheme here, we're going to end up now in the 2p subshell, right? Which now we got an availability of, we could place 6 more electrons before we would have to actually move on, right? So let's continue on then. Let's do number 5, which is boron. Has 5 protons, has 5 electrons. Once again, always starting back up here on top. So 1s2, zigzagging back, 2s2 there, zigzagging back, and now 2p1, yeah? If we were kind of going to look at the picture of this, we would have a box for the 1s, we would have a box for the 2s, and how many boxes should I have for the 2p? How many orbitals are in a 2p subshell? 3 of them, yeah? So we actually would have not 1, not 2, but 3 boxes, and those would represent, for example, the 2p subshell. Visually, this is where we're at. We filled this, and now we put 1 electron in there. You can see we got some room for some more in this case. By the way, at this point, how many electrons do I have on the second energy level? I actually have, this is the second energy level 2, and this guy is on the second energy level as well, and 1 more makes 3. So I have 3 on the second energy level, and I have still 2, obviously, on the first energy level. Any questions on that so far? All right, let's continue on, knock out the first 10. Why not? We'll go carbon next. So carbon has 6 protons, and that means it would have 6 electrons. So once again, always starting up here, we'll go with our 1s2, zigzagging back, 2s2, and here to our 2p, 2p2. Again, if you just count the top numbers, 2, 4, and 6, which is the 6 electrons, I am now up to 4 electrons on the second energy level and 2 on the first energy level here. Again, if you want to kind of look at the picture here of the orbital diagram, kind of looks something like this. 1 up, 1 down, 1 up, 1 down. By the way, not for our purposes, you don't have to worry too much about this at all, but when you do have a subshell that has individual orbitals, there's another rule that tells us the way they go in is actually up, and then the next one to actually go up in the next orbital. So they actually fill upwards first, and then they come back and kind of pair off going in the other direction. Not super important at all for our purposes here, but that's how they kind of fill the orbitals. That's what is known as Hund's rule, but again, not important for us here. Continuing on, carbon is nitrogen, and that is 7 protons, which means it should have 7 electrons. And again, starting up here, up on top, like always, will come 1s2, zigzag back, 2s2, and again, zigzag back, and now we're at 2p3. We are now up to 5 electrons on the second energy level, 2 and 3. And again, picture-wise, this is what it's going to kind of look like. Up, down, up, down, up, up, and up. By the way, how many more electrons can I put in that 2p subshell before it is filled? Yeah, 3 more, right? So I put 3 in. Again, they go in basically one at a time. Now can go back and pair up each of those with one going kind of in the other direction. So we'll continue out there. Oxygen, which is 8. Oxygen is 8 protons. It would have 8 electrons. Again, starting up there at the top, we'll go 1s2. Zigzagging this way, 2s2. And now coming this way, 2p4 in this case. Again, kind of continuing on our visual here. These guys are still filled. And again, up, up, up. And actually it comes back to the first one in the opposite direction. Now that first orbital there on the left is now completely filled, right? You can't put any more electrons on that first orbital over here. This guy is filled. The next ones obviously has to go to the next ones. We have room for 2 more, so let's finish out the first 10 here. Fluorine, which is 9 electrons. And again, starting up there on top, 1s2, 2s2, 2p5. And by the way, again, that is how you should write it. Once again, there is no like commas between things, no dashes. People like to do all kinds of weird things when they write it. So no dashes, no commas. And that's how you say it too. 1s2, 2s2, 2p5. That's how you kind of say the electron configuration. At this point on the second energy level, we got 2 there and 5 there. We have 7 electrons hanging out on the second energy level. As you can see from the electron configuration, we have 2 in the s orbital on the second energy level, and we have 5 electrons hanging out in the p subshell, those p orbitals on the second energy level. And if we were to do this, up, down, up, down, up, 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 down, and down, we have now filled up both of those orbitals, right? So for our p subshell, we got only one more spot to fill before it is completely filled, and that would be neon, where that happens. Maybe I'll just go underneath here, just put it on this page. Neon has 10 electrons because it has 10 protons. So again, would be 1s2, 2s2, 2p6 at this point. And again, if we draw it, squeeze it in maybe. Up, down, up, down, up, 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 down, down, and down. And now we are completely filled. My next electrons would end up where? Following this way, that would be where the next ones would continue on, yeah? Question on how to write that there. Again, you don't have to pictures or anything like that, just for visually so you can see it. That actually is something, so you know that again is what's referred to as orbital diagram, as to how another way to kind of just one here. Once you try calcium, which is 20 electrons. So why don't you write the electron configuration for okay, let's take a look. I hear a lot of chatting, so let's take a look and see how we're doing. All right, so we're going to start at the top here always. So we're going to roll obviously first into our 1s orbital, and we obviously can fill it with 2 electrons. So we put 2 in. We still got 18 to go, right? So we're going to zigzag back around. We're then going to hit our 2s, right? And that also could hold a maximum of 2 electrons. So again, if we just count the top, we're at 4 electrons. We still got 16 to go. That means we're going to then zigzag back here to our p subshell, 2p subshell. And we know that the 2p subshell could max out at 6 electrons, which we definitely will fill. Once again, if you're not sure, if you count up the top numbers, we're up to 2, 4, and 6 is 10. We're halfway there. We then need to travel down to our 3s, and because that's an s orbital, it could only hold 2. So we'll definitely fill that guy. So now we're at 12 electrons by counting the top. And now we're going to zigzag back into our 3p subshell. Once again, it's a p subshell, which means it could hold 6, and we need all 6 of those filled. So that's going to be a 3p6. Once again, if we count up the top numbers, 2, 4, and 6 is 10, plus another 2 is 12, and 12 and 6 is 18. So we're almost there, right? So we got 2 more to go. And remember, this is the part people mess up on. It actually goes to where next? The 4s, not the 3d. So it goes to the 4s next. And that's an s orbital that can hold 2. And there it is, yeah? Question on that configuration. How many electrons do I have on the 4th energy level? 2. Those are the highest energy levels in calcium, right? Those are basically its valence electrons, those 2 electrons out there. All the rest of them are considered core electrons closer to the nucleus. Now, when you write electron configuration, sometimes people will use sort of a shorthand electron configuration, or the way that they write it. And the way that sort of you could write electron configuration in sort of a shorthand way is you go to group 8 on the periodic table. We talked about the periodic table, I think, right? Group 8 are the what things? Group 8 are the noble gases, yeah? And when we look at electron configuration, for example, for calcium that we just wrote, if I look just through here, how many electrons is that again? That is 18 electrons. And who on the periodic table is number 18? It is argon. Argon is a noble gas, which means you could shorthand this electron configuration by putting argon in brackets. And what that means is that's like argon's electron configuration. And continuing with the rest of it, the 4s2. So that's sort of a shorthand method that's sometimes used for electron configuration, especially kind of the longer one. I'm going to shorthand it a little bit. But it's important to know that what needs to go in the bracket is always a noble gas. So it always has to be a noble gas that comes right before the element you're writing the electron configuration. So wherever your element is, go backwards to group 8, and whatever noble gas comes before it, you could kind of shorthand it. So for example, if we did sodium, which is 11, right? And we followed our chart here, we would end up with 1s2, right? Coming this way. 2s2, zigzagging back. 2p6, zigzagging. And now 3s1, right? And if we count up the top numbers, we have 2, 4, 10, and 11. Once again, if we look at where sodium is on the periodic table, right about here, we go backwards to the noble gas over here in group 8. It is neon. And neon is what atomic number? Is number 10. And that means this part of the configuration that counts up to 10 electrons is equal to neon's configuration. So you could shorthand this by going, all this basically is neon and 3s1. So again, that's another way sometimes electron configuration is written. Sometimes people call it noble gas configuration. It's a shorthand method always has to be a noble gas in the brackets. And again, always has to be a noble gas that's before the element. It can't be after, so it's got to be before the element. And then you basically just pick up from the noble gases configuration, however many electrons that is, and you continue on. Any questions on that there? Now, let's say you had iron, which is 26. What would the electron configuration? Okay, let's take a look. Again, going to start up here. So we're going to come here to our 1s2. We're going to zigzag back 2s2. Coming back around here. We know we could put 6 in a p. Coming to our 3s2. We take a stop there to figure out how many we put on there, and we're only at 12, right? So we got a little bit ways to go here. We're going to continue this way to our 3p, which we could put 6 in. So we're at 18. Again, we go then to our 4s next. And now we're at 20, right? And now we zigzag back to the 3D, right? And that would be 3d6 in this case, yeah? Again, the 4s, again, does come before the 3D, yeah? And those s's always kind of come before the d's. It's just the way, energy-wise, it happens. And that thing down through here is how many electrons again? That is 18. And if we look at iron and go backwards on the periodic table, 18 is argon. 4s2, 3d6, yeah? So again, that's kind of a shorthand way you could kind of do that. And you could probably see why perhaps they've invented the shorthand. They don't want to write it all out, right? And that's the purpose of it. Now, if you follow this chart here, and again, I showed you how you could kind of make that. And again, you can make it by just simply, or basically, right? And just putting the numbers underneath it. You should be able to write any electron configuration you want. There are 2 exceptions. Actually, there's lots of exceptions, but for us, there's 2 exceptions you should be aware of that if you follow this, you will not get really what is considered the stable configuration for that. And that is chromium, which is number 24, and copper, which is 29. If you follow this chart, and if we do this kind of shorthand, you end up with argon 3d4 if you kind of follow the chart. And if you follow the chart, you would end up with argon 4s2 3d9. It's been found experimentally that chromium and copper are actually a lot more stable with an extra electron in the d orbital and one less electron actually in the s orbital. And they're actually able to do that because honestly, those orbitals in terms of energy, they're like super close to each other. So it doesn't take a lot for them to kind of pop up and pop down in energy level. And actually what happens, just not to hopefully confuse too much, when you're putting electrons in the d orbital, they actually do switch in energy actually. And what ends up happening is they switch in energy after you put some electrons in those Ds, and the 4s ends up being higher in energy than like the 3D. And that's important, for example, for transition metals when they lose electrons, which ones gets lost first. So there is a kind of switch that occurs when you do that. And that's why sometimes if you look around, maybe on some other resources, you will sometimes see people write electron configuration like all in order, like all the 3s are together and all the 4s are together. And they do that because they're writing electron configuration based on energy. And that's what happens after the electrons are basically in the atom. But in any chemistry class you take, including this one, we write it based on filling order, which again, the S's should get the electrons first and then the D's. But in case you actually see it somewhere, technically it's not wrong. It's actually correct in terms of energy, but in terms of filling order, the S's should actually go first and then the D's should come next. So the correct configuration for chromium is argon 4s1 3d5. And what that essentially does, if you just think about the boxes we were drawing, it actually puts an electron in each of the d orbitals, all heading in the same direction, and it makes it really, really more stable. Anytime you could get like the electrons all kind of going in the same direction, like those arrows pointing in the same direction, it kind of helps with stability. And the same sort of exception happens over here for copper, one less electron in the s and one more electron in the e. And that also will fill up the d orbital there for copper, and also when it flips over, it'll have that one electron hanging up there in the 4s, which makes it a little bit more stable. So those are two that you are responsible to know: chromium and copper. Look on the periodic table where chromium is and copper is, and you go down on those elements and in, there's a ton of exceptions in those areas. For example, PD, which is kind of in there to the left of silver, it actually has no electrons in the s. They've all went up to the d and stuff like that. So, but for our purposes here, you're only responsible to know chromium and copper's exception. Everybody else, you could just follow the little zigzag thing and write it like normal and stuff like that. First off, any questions on that there? Okay, now let's just talk just really briefly about, since we talked about ions previously, and it's kind of important for bonding coming up. Ions, again, as we talked about, there's two types. There's cations, right? And there's anions. And as we talked about, cations are positively charged and they lose electrons. Anions are negatively charged, and that's because they gain electrons. They essentially have more electrons than protons, so that's why they become more negative. So if you have an ion and you want to write an electron configuration for it, you do have to adjust the electron configuration for its charge. So we take oxygen, which is neutral, and oxygen is 8 electrons in its neutral state. When oxygen forms a charge, it's -2. And what that means is it has gained 2 electrons. Of 8 electrons, it actually will have 10 electrons, which means if we were going to write the electron configuration for oxygen with a -2 charge, it should be 1s2, 2s2, 2p6, right? And if we look at something like sodium that we just looked at, sodium with no charge has 11 electrons. Sodium typically makes a +1 charge, and the plus means that it has lost electrons, and 1 is how many it lost, which means 10 electrons. And its configuration would be 1. Do they both now have the same electron configuration? They do, right? By the way, who else has 10 electrons on the periodic table? Neon, yeah. So neon, oxygen charge, and sodium with a +1 charge, they all have the same electron configuration. That is what is known as isoelectronic with each other. Yeah. Why is that important? As we'll talk about in the next chapter, that is really the whole reason for bonding taking place. So for example, the way that sodium can become very stable is it has to lose an electron, and it actually backs up on the periodic table to the noble gas that comes right before it. And oxygen, by gaining 2 electrons, goes forward on the periodic table to the same noble gas in this case that comes after it. Why does everybody want to be like the noble gases? They're chemically inert, they're super stable. And that is the basis of all bonding: ionic bonding, where we don't share electrons; covalent bonding, when we do share electrons. The whole purpose of bonding, in a sense, is for everybody to end up with the same electron configuration as the noble gases, because everybody wants to be like them. Everybody wants to be that stable. And the way that metals and nonmetals could do that is by gaining and losing electrons. When metals lose electrons, they back up on the periodic table to the noble gas that comes before them. When nonmetals gain electrons, they go forward on the periodic table and they end up with the same electron configurations as noble gases. So that's a really important sort of aspect of what happens in bonding, is for everybody to achieve the same electron configuration as the noble gases, and makes a really stable situation and a stable bond. They actually don't, which is a really important thing to remember. They do not become neon. Each of those things do not become neon, because in order for them to become neon, what would have to change? What is the thing that tells you what type of element it is, or what element it is? Protons, yeah. So we didn't change the protons in oxygen. We didn't change the protons in sodium. The only thing that changed is their electron arrangement, and they have a much better electron arrangement, like the noble gases now, and a much more stable one. So sometimes people think they become those elements, and they don't, because we didn't do anything with the protons. We just changed their electrons. Any questions on that? So if something does have a charge and it's a representative element, it will back up or go forward to the noble gas before it or after it. We won't get into transition metals in terms of charges, but they actually don't do that. It's a little bit more complicated what happens with them. We're not going to worry about it here in this class, but they actually will lose the s electrons first and then the d electrons. They technically have upwards of 12 valence electrons or high electrons, depending on which one you're looking at. Any questions there? All right, I'll just take on here. So again, a reminder that that chart can easily be sort of made on any paper by, again, just remembering 1, 2, 3, 4. So as I showed you a second ago, you just want to go 1s, 2p, 3d, and 4f. And again, at that point, you just got to put the numbers underneath like we talked about. You go 2s, again, just keep the same letter, obviously, all the way down. You could go to 7 if you want on all of them. Definitely the first two, you should go to 7. And then do the same thing for the other 3p, 4p, 5p, 6p, and 7p. Again, 4f, 3d, 4d, 5d, and 6d. Again, if you went to 7 on that, no big deal. Like I said earlier, you're probably not going to get there. And then 5f. And now you have, again, just draw your arrows. And you basically have the exact same chart we've been using that will take you through all that. So again, being able just to recreate that for yourself really quickly is a pretty good thing to know. Again, along with what we've been talking about, S2 electrons, P subshell 6, D subshell 10, and F subshell 14. All right, so a couple other things about electron configuration here and like the periodic table. If we look at the periodic table, you can sort of use the periodic table to figure out electron configuration. And let's take a look at that. In the first two groups on the periodic table, that is what is referred to as the S block. And that is because S could hold how many electrons? 2. So 1 and 2, yeah? Groups 3 through 8 is the P block, and the P block could hold 6. 1, 2, 3, 4, 5, and 6. The transition metals are the D block. They could hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And those two rows on the bottom are the F block. They could hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So if you know what you're doing, you could actually use the periodic table to do electron configuration. There's those periods, right, that go this way, like 1, 2, 3, 4, 5, 6, and 7, just like energy levels. And that's what those periods represent in terms of the energy level, since there's 7 of them. So for example, if we have a real periodic table here, right, and we have our 7 periods over here, and again, let's say we wanted to do the electron configuration for sodium that we did before, right? So sodium is right here, number 11. Blow it up a little bit, maybe. So sodium is right here. So what we would do in this case is you would start at the top, and I don't know, we'll go this way with it. Maybe actually let's do this. That might work. We're going to start here. This would be 1s1 through hydrogen all the way across to helium. That would be 1s2. We're now here at 2. This is 2s2. This is 2p6. I guess I should write that as I'm doing it. That might be good. I'll do that. Maybe it'll come up. There it is. So again, 1s2 to here, 2s2 to there. This is now 2p6 all the way to neon. This is now 3s, and we only go in one spot. 3s1, yeah? And that would be the electron configuration. Let's say we wanted to do phosphorus, right? Same deal, starting back up here, 1s2 all the way across, 2s2, 2p6, 3s2, and now we're coming to phosphorus, which is 1 box, 2 boxes, and 3 boxes in, and that's the 3p subshell. And now we have phosphorus, yeah? Now, you do have to be careful, and I said you do need to kind of know what you're doing if you want to count off the electron configuration. Gets a little dicey perhaps in the transition metal region. So let's talk about why it gets dicey. Let's do iron, which we did the electron configuration earlier of, right? So let me erase some of this here. All right, so if we're going to do iron, we'll start here again. Starting at the top, 1s2 to helium, 2s2 there. This is still on the second period, and that's the P, so 2p6 all the way to neon if you count the boxes. 3s2, 3p6 all the way there. 4s2, right, which is good. Yeah. And now we want to get to iron, which is in the D subblock, right? We can count the boxes, 1, 2, 3, 4, 5, and 6. D6, what should the number be in front of it? Should actually be 3, yeah? Because remember, d orbitals actually start on the third energy level. And right here is actually the 3d. This is the 4d. This is the 5d. And this is the 6d. They are 1 behind the period number. So that's period 4. They're actually 1 behind. So you got to be a little careful if you kind of go into that area and you want to try to count it off the periodic table. Also problematic, which probably you won't get to too much in this class, but down here, remember that these 2 rows technically go right there, yeah? And that's the 6th and 7th period. But this is 4F. That's where the F start, right? And this row here is 5F. So it's actually 2 behind the period number. So middle area, a little crazy, you know, you got to make sure you understand, you know, for you guys, I don't think you're going to get too much on the bottom there, but definitely you got to understand that if you get to this guy and you're counting, that's 3D. Down here, that would be 4D. 5D and 6D. Again, I would probably recommend the zigzag thing. You probably won't make too many errors in that. But, you know, if you want to try to do it that way, that's another way you could kind of use the periodic table and figure out the electron configuration. Any questions on that there? Yeah. You just got to be careful of those spots. Yeah. All right. That we talked about. All right, so let's talk a little bit about valence electrons. And valence electrons are important because they are the highest energy level electrons in an atom. And the importance of the valence electrons, we'll definitely talk more about in the next chapter, is they are the ones involved in bonding. So they are really the only electrons involved in bonding. So when we look at nitrogen and write its electron configuration for 1s2, 2s2, 2p3. When we look at it, as we talked about, I think when we were doing it, it has 5 higher energy electrons, those guys right there, and those would be the valence electrons in nitrogen. Again, the lower energy electrons are sometimes referred to as core electrons. And the core electrons, as we'll talk about, are held a lot tighter next to the nucleus, and they are not involved in bonding. So again, only those valence electrons are involved in bonding. If you looked at lithium that we saw earlier, 1s2, 2s1, again, this is the highest energy level. There it is. It has one valence electron. And this would be the core electrons. So you could definitely write the electron configuration. And typically speaking, the valence electrons will usually be the last ones that you write in electron configuration. For sure, on the ones on the outside is typically for sure. Transition metal is a little bit different. I keep looking that way like there's a periodic table. It's on that wall in this classroom. But you typically can do that. But who really wants to write electron configuration sometimes when you want to know how many valence electrons something has? So the easier way to figure out valence electrons is the number of valence electrons equals the group number. Yeah. So if we look at lithium, we find lithium in group number 1 on the periodic table, which means it has one valence electron. Nitrogen is in group number 5 on the periodic table. Yeah, N right there, number 5. So it has 5 valence electrons. So that is a much easier way to figure out the valence electrons, which is, I had that periodic table there. Here is nitrogen in group number 5, right? 4, 3, 2, not 2, that's bad counting. 6, 7, and 8, 1, and 2, right? Now, everybody in group 8 has 8 valence electrons except for which one? Helium. Because helium only has a total of 2, so it can't have 8, obviously, right? So it's only got 2. So helium has 2 valence electrons, which are the only electrons it has, because the electron configuration for helium is 1s2, right? So those are the 2 valence electrons, the only ones it has. Everybody else in group 8 will have 8 valence electrons. That is why, as we'll talk about when we get into bonding, our friend hydrogen should only have 2 electrons because he only needs to get to helium to become noble gas configuration. So that's why hydrogen only makes 2 electrons, or should only have 2 electrons when it does bonding. All right, so we could definitely look at the group number for our valence electrons. And again, fluorine, which is group 7, has 7. Chlorine, which is group 7, has 7. And carbon, which is group 4, has 4 valence electrons as well. Now, the transition metals is also equal to the group number, except that you need to use the 1 through 18 numbering. And I probably should have stayed on that picture. So I'm going to go back there. Come here. Oh, too far. Come back. There we go. We're scribbling on that. So these are our transition metals. And really, we use the kind of 1 through 18 numbering. These numbers here are the valence electrons for transition metals. The good thing is, in normal situations, we really don't use it too much in bonding, so you don't have to worry too much about it. But those are the numbers. And why is that? We'll take a look at iron, for example. Iron, again, was argon, right? 4s2, 3d, 1, 2, 3, 4, 5, 6. All of these are actually iron's valence electrons. And what happens, as I mentioned just briefly, is we know that when they go into the atom, they do fill the S first and then the D. So it pops as 1, 2, 3, 4, 5, and 6. But what happens, as I mentioned, is they do switch in energy. So transition metals are a little bit different. They will actually always, when they make or lose electrons, 1, 2, 3, 4, 5, and 6, they will always take out the s electrons first when they lose electrons. So those are always ends up being the highest energy level, and they'll take them first. But then if they need to, they have all these d electrons available to them to also lose. So something like iron, for example, could lose 2 electrons and become iron with a +2 charge, which it would lose to just as 2s electrons there. And iron could also become +3 charge, which it would lose to 2s electrons there and the 4s orbital, and then one of the d electrons that are available to it. So it technically has that many electrons, those guys, and they always will lose those s electrons first when they lose electrons, and then if they need to lose more electrons, they go into the d. So that's what happens with those. But in terms of valence electrons, you kind of just use the 1 through 18 numbering for that little range there, and I'll tell you those valence electrons for those guys. All right, let's see here, valence electrons. So metals and nonmetals on the periodic table in terms of reactivity, as you go up a group, especially metals, they tend to give up their electrons more easily. I'm sorry, as you go down a group, I said that backwards. As you go down a group, they tend to give up their electrons a lot easier. So the most reactive metal that you could find on the periodic table is located right there bottom left corner of the periodic table is the most reactive metal that you can find. Nonmetals are opposite. They tend to like to keep their electrons and gain electrons. Upper right of the periodic table, our friend fluorine there is the most reactive nonmetal you could have for some reasons we're going to talk about right now. Some of these periodic trends we're going to talk about here is the reason why that occurs. So let's talk about a few trends on the periodic table. The first trend is what is known as, and we'll do Z effective or effective nuclear charge. And we'll just use a very simple explanation of this. And the simple explanation is if we take lithium, which has 1s2, 2s1, right, in terms of its electron configuration. Lithium is group number 1, which means it has 1 valence electron, and that is its valence electron. This is core electrons. So lithium has 3 protons, which means its nucleus has a +3 charge, right? 1 plus for each proton that's hanging out in there. So if we just think about our core electrons here, on the first energy level, I'll just draw it like this, even though they're not going to probably be hanging out like that, but we'll just draw it for the picture like this. They are really close to the nucleus, right? Then we have that one lonely valence electron hanging out a little further away from the nucleus. So what happens is, as I mentioned, the positive charge and negative charge and the attraction between those two things, it increases with size. So if you have something that's like +3 and -3, again, it's going to be held together a lot tighter than if you had something like +1 and -1. So the bigger the charge, the stronger the attraction is. So when we look at these core electrons, they are sitting pretty much right close to the nucleus. So they're going to feel that full force of the +3 attraction, which is going to be a pretty strong attraction for them. It's going to hold them pretty tight. But when we look at the valence electron of here, which is in higher energy level, a little further away from the nucleus, it is going to experience what is known as shielding. And what is shielding? Well, shielding is we have those lower energy electrons in the way of the nucleus's positive charge. So like you go into the movie theater and sit down, nice, perfect seat in the screen, right? And right before the movie starts, somebody comes and sits with a giant hat right in front of you and shields out half the screen, right? So you're not be able to see the entire screen. So the same sort of thing happens here with those electrons in the lower energy level. They're basically providing a wall, if you will, of that positive charge, blocking some of that positive charge from actually reaching that valence electron, which is a little further out. You could actually calculate it, which you will never be asked to do, but just to demonstrate what it is happening here, we could take the +3 charge, which comes from the protons in the nucleus, and we could subtract how many electrons are in front of that guy that's in the outside, and there's 2. And ultimately, what that electron out here is actually feeling is instead of a +3 attraction, which is a pretty strong attraction, it's actually only feeling like a +1 attraction to the nucleus. So it's still attracted to it, but not as tightly as those lower energy electrons are to the nucleus. So what does that mean? That means that valence electron is not going to be held as tightly, right? And again, that's why one of the reasons why it can be kind of lost and given away in bonding, while the core electrons, which is feeling the full brunt of that positive attraction, is kind of stuck, right? They're not going to pretty much go anywhere. They're not going to be involved in bonding. So what happens is, in terms of Z effective on the periodic table, is it increases as you go up and to the right and decreases as you go to the left. And the reason it increases as you go to the right on the periodic table is there's a lot more protons on the right? The atomic number gets bigger. That means the positive charge in that nucleus is bigger. So even the outer electrons, which are further away, will still, through that Z effective, even though they're not feeling the full brunt, still going to feel a pretty good positive charge and attraction and be pulled in closer to the nucleus. That also affects the size of the atom. Because of that getting pulled in more to the right, we typically will see this overall size of the atom be smaller because even the outer electrons are going to feel a bigger positive pull towards the nucleus and going to kind of bring everybody in and smaller overall. Another important trend is ionization energy, which clearly I scribbled all over. So we'll get rid of that. Ionization energy is the energy required to remove an electron. And by the way, electrons actually do come off one at a time. So they don't all just drop off at once. So for example, if you take something like magnesium, the first thing that will happen is magnesium will just lose one electron basically and become +1 charged. That is what is known as the first ionization energy. And that's the energy basically just to remove the first electron. What happens next is that magnesium that's already lost an electron will then lose a second electron. And that is what is known as the second ionization energy. And that is, like the name implies, the energy required to remove the second electron. And, maybe it goes one more or not, and it loses one more electron. And that is what is referred to as the third ionization energy. If you had to take a guess, is it easier to remove the first electron or the last electron? Which one should be easier to remove? It's actually the first one, right? The first one is neutral, right? So those electrons are out. When you lose the first electron, what happens to the electron density? Everybody gets brought in, right? You lose some of those electrons. So the overall size of the ion in this case, which would be positive, actually gets smaller because everybody gets pushed back in. Because of that, they're now closer to the nucleus, right? The next electron you want to remove takes more energy. You remove the second one, what happens? Gets smaller again, right? Now those outer electrons are even closer. So it gets progressively harder every time you remove an electron because the overall size starts to shrink. And again, those outer electrons are now moving closer to that positive charge that's going to hold them a lot tighter. So the general trend for the first ionization energy is it increases as you go up and to the right, and it decreases as you go down and to the left. And the first ionization energy is a lot less than the second to remove the second electron, a lot less the second one than the third ionization energy. So the ionization energy from first, second, third, however many you want, gets higher and higher every time you pop off an electron because it gets harder and harder to remove those electrons as you go through it. That, by the way, is why magnesium, for example, over there, magnesium, it will only make a +2 charge. And why is that? If we look at the electron configuration for magnesium, 1s2, 2s2, 2p6, 3s2. Magnesium is group number 2. How many valence electrons does it have? 2. And that would be these right here. So once we lose the 2 valence electrons, right? That gives us our +2 charge. We're now into core electrons, which at this point is even closer to the nucleus. Good luck trying to remove that. It's not going to happen. So like, for example, the energy to remove that second electron for magnesium is like 1,000 kilojoules of energy. It jumps up to maybe like, 7,500 kilojoules, and it goes up almost like 5-fold. You need like a ton of it. That's why, for example, something like aluminum only makes a +3 charge. Aluminum, to remove like the third electron, which is still a valence electron for aluminum, is something like maybe, I don't know, off the top of my head, is something like 2,000 kilojoules of energy. When you try to remove the fourth electron, you jump up to almost like 12,000 kilojoules of energy. So it's not going to happen under a normal condition. And that's why certain things, for example, will have fixed positive charges, because as soon as you get rid of those valence electrons, you're not going to be able to rip out any of those core electrons because they're now way closer to the nucleus and going to be held a lot tighter, and just energy inefficient to try to do that. It's just not going to happen. Any questions on that? Now, a couple other important trends, electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, it increases as you go up and to the right. Fluorine is the most electronegative element you could have, and it decreases as you go this way. So it increases and decreases. Also, electron affinity, which is actually different than electronegativity. That is the energy change when an atom gains an electron. And on the periodic table, that also increases up and to the right and decreases down and to the left. So electron affinity is when somebody gains electrons. If you have an affinity for something, that means you like to gain electrons, basically. So if you have high electron affinity, that means you're pretty much willing to gain electrons, pick up electrons. And electronegativity is the ability just to, if you see an electron near you, have the ability to bring it towards you and kind of drag it towards your direction. And because you have the great amount of ability to drag an electron towards you, you probably are going to be able to accept that electron and have a high electron affinity and be able to sort of pick up those electrons. Any questions on either of those? We will see electronegativity a lot in bonding. It's a very important concept for bonding and how electrons are shared between atoms when we look at it. Now, the last sort of trend is atomic size. And as you go up and to the right on the periodic table, the size of the atom gets smaller. And one of the reasons is that effective nuclear charge, because you have a lot more protons in the nucleus, even the outer electrons are going to kind of be drawn closer to the nucleus. Size increases as you go down and to the left. And that's because as you go down into the left, you just have a lot more electrons there, and there's just nowhere to put them except on higher energy levels. So they're going to be further spread out, and that's going to cause the atom to be a lot larger. So what does all these things tell us when we look at just a blank periodic table square? If we take all these trends together, the effective nuclear charge, which increases as you go this way on the periodic table and decreases this way. The ionization energy, which is the energy to remove an electron, increases as you go this way and decreases as you go this way. The electron affinity, which again is the energy change that occurs when somebody gains an electron, increases this way, decreases this way. And electronegativity increases this way and decreases this way. And lastly, size decreases up and to the right and increases left and down. What this tells us, if we overlay this to what elements are where on the periodic table, when we go to the upper right of the periodic table, those are our friends, the nonmetals, right? And what nonmetals have in common is they are very small in size, which means even the outer electrons are close to the nucleus. They have very high ionization energy, which means you got to put a ton of energy in there to try to rip out an electron from them, and it's not going to happen. They have very high electron affinity, which means they're very good at accepting electrons. And they have high electronegativity, which means they're very good at not only keeping their electrons, but taking somebody else's electrons, essentially. So what that tells us is nonmetals are typically the elements that like to gain electrons and become negatively charged, right? Now, if we look at all these periodic trends and go bottom left of the periodic table, this is where we have our metals, right? And that's where our metals are located. And as we go left and down on the periodic table, we have a bigger size atom. which means the outer electrons are further away from the nucleus. They're not held as tightly. They have very low ionization energy, which means you could just ask them really nicely and they're just going to give away their electrons and don't care about it. You don't have a lot of energy to do that. They have very low electron affinity. They have very low electronegativity, which both mean they have no interest in basically bringing electrons towards themselves. So they're all about take my electron, please, right? Is basically what metals are. And they're more apt because of these periodic trends to give away their electrons and lose electrons. And they typically will lose electrons and become positively charged. That is why when we talk about bonding, which we'll talk about in the next chapter, when you take something that's a metal, which has all these properties of take my electrons, please, with a non-metal on the opposite side of the periodic table that has all these properties of I would like to keep my electrons and also take your electrons. When those two guys get together, what happens is the metal goes, take my electron. He gives away his electron. The non-metal goes, thank you. And we get a transfer of electron. And that is how ions form. We get the metal that now becomes positively charged because he lost electrons. The non-metal now becomes negatively charged because he gained those electrons. And now they're attracted to each other because they both have a charge, right? And that is basically what an ionic bond is. Now, what happens when we do a covalent bond is we're actually putting together two nonmetals, and nonmetals are all located in the same area on the periodic table, which means both of those nonmetals have the same properties or similar properties. Neither one of them is going to want to give away its electrons. They both are looking to gain electrons, right? And hang on to their electrons. So what happens when two nonmetals come together is they have a nice conversation and they go, we'll just decide to share rather than anybody giving up their electrons. So the best that they could do is because they both want to keep their electrons is decide, why don't we just like share the electrons, right? And that type of bonding is covalent bonding, where we share electrons, and that happens when two nonmetals get together because they both have the same sort of periodic trends. They both want to keep their electrons, they want to gain electrons. Nobody's going to give away their electrons, they're going to share. And again, that's very opposite than the other type of bonding, which is ionic, where you have the very big difference in take my electrons, no problem, I'll be happy to do so. We get a transfer of electrons. So these trends are really important for why we get these different types of bonding that occur that obviously we'll talk in the next chapter obviously about as well. Any questions on those trends there? Yeah. Now, speaking of bonding, one of the ways that we do represent bonding is with Lewis dot symbols. They are sometimes referred to as just generically electron dot symbols. They were called Lewis dot symbols and Lewis structures because a guy named Lewis kind of did a lot of things with bonding. What are Lewis dot symbols? Remember that as we talked about, only valence electrons are shown in bonding and are involved in bonding. So Lewis dot symbols are basically the symbol for the element and basically one dot for each valence electron it has. And as we talked about super quickly, we could figure out the number of valence electrons by the group number, right? So it's equal to the group number. So there is no real rule about the dots other than you cannot usually put more than 2 dots per side, yeah? By the way, there's 4 sides to my symbol, and there's 2 dots per side. That is what number? That is 8. Who again on the periodic table is 8? Yeah, the noble gases, right? The guys at the very end. And again, as I mentioned earlier, that is, we'll talk about the ultimate goal of bonding is again to get to that electron configuration like the noble gases. And that's what's known as the octet rule that we'll talk about. But essentially, everybody wants to do that. So a lot of times people will just kind of go clockwise, want to, and then put them the rest there. So for example, here, if we had lithium, which is group number 1, it would have 1 valence electron. Hydrogen has 1 valence electron. We have oxygen, which is group number 6. It would have 6 valence electrons around it. And we use these Lewis dot symbols to help us understand bonding and what's going on in bonding. Here is a chart of all that. And I made it one day when I was bored. I should really get a hobby. But again, these are the Lewis dot symbols for all the elements. The transition metals are sort of grayed out there because we really don't deal with transition metals and bonding or having to draw anything with transition metals. So that's a good thing. And a couple of things that we talked about as we did before. Again, hydrogen only needs to get to helium, so it has 2. Everybody else, again, the goal of bonding is right there to end up with the same electron configuration as those guys in the noble gases. That is chapter 4.